We're now going to discuss the concept of interrupt. In most microcontrollers, the interrupt is a mechanism that enables the peripheral to stop the regular execution of your processor and execute a piece of code that will service a very special request. Think about it, for instance, as on a serial port, you might want, as soon as a message comes in, you might want to stop your processor and read this message and service that. So the process involves suspending the current task, saving its context, branching to a very specific piece of code that we call the exception handler, and then, once you're done, resuming back your regular operation. You have to think about it as a function call that is triggered not as part of your regular processor execution, but by a third party. A peripheral will say, hey, I need you to execute this very specific piece of code and use that to process some information for me. A distinction should be made between exceptions and interrupts. While they are similar in nature in the way you process them, interrupts are coming from external sources to the processor core, such as a peripheral, while exceptions are generated inside of your processor core as a result of a hard fault, such as a division by zero, for instance. Interrupts are processed through the interrupt handling concept. Once a peripheral needs to notify the CPU to halt its operation and process a very specific piece of code, the interrupt request line is raised. The RRQ line is simply a metal line that contains a digital signal that triggers something in the processor. Once the RRQ request is made, the processor will stop its execution flow, so it will stop its main thread and jump into the handler mode. You can see the handler mode as a second thread that will execute and that will basically service your request. Once this is done, the interrupt returns and the main thread is resumed. In order to jump from the main thread into the handler mode, you need to implement some processor status and register save mechanism and restore back once you're done. This is done through the stack. Some definition to understand better what the interrupts are. The first one to consider is the interrupt request, or RRQ. RRQs are used to categorize or to rank, if you prefer, some exception types associated with a peripheral. As part of our Cortex-M processor, we have 32 RRQ inputs, so 32 potential different sources for an interrupt. We also have non-maskable interrupts. Interrupts can be masked, which means that you can decide that you want to disable them because they're not critical to your application or you want to execute something specific. Some of them cannot be disabled. Those are the NMI, and they are associated with the highest priority level. So not only they can't be disabled, but they will have a higher priority than any other interrupt. And you will typically use these interrupts, or I should say a vendor will typically use these interrupts to support fundamental peripherals such as a watchdog timer that monitors the proper execution of your code, or a brownout detector that will detect any voltage drops on the power supply. The handlers are the software code that gets executed once an interrupt is received, and the concept of nested interrupts means that we might have interrupts that do interrupt an interrupt. So that brings in the concept of priorities, interrupt priorities, where a higher priority interrupt will be able to stop the execution of a lower priority interrupt. So how do interrupts work? In order to be processed, you need to add some specific hardware. This hardware, in the context of our ARM processor, is called the Nested Vectored Interrupt Controller. It's basically an additional module that is part of your Cortex-M processor and that can do the following things. First of all, it interfaces with the processor core and is able to halt the processor execution and make it jump to some other portion of the code. It also interfaces with the other microcontrollers, or the peripherals of the microcontroller, and basically aggregate all the interrupt request conditions, perform some arbitration. It also gets a system exemption, and decides to make the arbitration which one should be processed first and to which part of the code the processor should jump. Interrupts and exceptions are categorized by some exception numbers. As part of the ARM NVIC, we do have 47 different exception numbers which start from the exceptions. The exceptions coming from the processor core are here to deal with odd faults as well as some system level interrupts that are going to be useful, for instance, to implement operating system. Every single exception number is associated with a priority. The highest priority is represented by the lowest number, and it starts with the reset vector. Once you reset your processor, you want that to have the highest priority, of course. This is immediately followed by the non-maskable interrupt with a priority of -2, followed by the odd fault. Other priorities will be programmable so that the user can decide which level of priority you must assign to which peripheral. So while this table represents the general truth of the NVIC controller, once you pick a microcontroller, this NVIC table will be mapped to your set of peripherals. And in the context of our processor, the NMI is linked to the clock security system that is here to check if your clock is stable or not. And all the different IRQs from 0 to 32 to 31, so the 32 IRQs from the peripherals will be mapped to different peripherals. Watchdog timer, programmable voltage detector like the Browner detector, USB, and so on and so forth. So the NVIC is a programmable unit that will allow your software to manage interrupt and exceptions. And in order to do so, as any other peripherals, you can control it through a set of memory mapped registers. And these memory mapped registers will be used to enable or disable each of the interrupts, because in your application you may not want your USB to trigger, for instance, an interrupt. You'll also be able to define the programmable priority levels, and you will also enable the software to access the pending status of each interrupt. So when you receive multiple interrupts, you'll be able to see which one has been triggered. Everything is finally controlled by the prime mask register. So if you remember, when we looked at the registers of our processor, the prime mask is one of the special registers that is used to disable all interrupt and exception with positive priorities. Remember that NMIs, odd faults, resets cannot be disabled, and that's in particular what we get here. Priority levels in our processor are associated to every single exception, and the priority level will affect whether the exception should be carried out or wait until later, in particular until the highest priority interrupt is executed. Our Cortex M0 does support 3 fixed highest priority level, the -3, -2, and -1 for reset, NMI, and odd fault, as well as 4 programmable levels that you can assign at will to your different RRQs and other exception sources. The priority levels are saved in an 8-bit wide register, and only the 2 MSBs are implemented. So technically, if you want to set your priority to 0, remember, the smallest, the highest priority, you will write a 0 in this register, then 40, 80, or C0, depending on the level that you want. Why do we only implement the 2 MSBs? Because the more complex Cortex-M processors, M3, M4, do have additional levels of priority, and you want to make sure that your code is compatible with that. So in those processors, you will implement bit 5, bit 4, and so on and so forth, but your 4 levels of priority that you used in a code written for the M0 will be immediately translated to M3 with almost no efforts. So what is the impact of priority levels? Well, it does impact how the processor is going to service your request. So think about it as the following scenario. If your processor is already servicing an interrupt, but does receive a new exception with a higher priority, then we will end up being in a preemption case. So the preemption will take place, and the running interrupt or exception is suspended, and the new exception lander is called, we enter in a so-called state of a nested interrupt. Once we're serviced, we will go back to our previous interrupt handler. However, if our new exception was having the same priority or lowest priority, we will wait until this interrupt is processed before entering into our new interrupt handler state, and that is creating a pending state. When I receive an interrupt coming from one of the IRQ or the exception, I must know which interrupt handler I'm going to go to. In order to do that, I have to save some sort of a pointer table that will point to the different functions I need to call when I have a specific event that triggered. This collection of pointers is called a vector table, and it's located at the very bottom of your memory space. If you remember correctly, in our memory space, at the first address, at address 0, we are saving the MSP initial vector, right? So the memory stack pointer. This is immediately followed by the reset vector. Oh well, now that I told you that reset is actually considered as the highest priority interrupt with a priority of -3, now we understand what's going on there. When we have a reset, our processor goes and look at the address pointed in this location, and then our code will jump there in order to start our main program operations. Well, very similar things do happen for the other interrupts. Once I do get this interrupt, my processor is going to look in this table, retrieve the address of the IRQ location, the interrupt handler location, and jump there. This vector table, as I said, at the bottom of the memory, which is part of our code memory space. So everything is set up at compilation time. When you start loading your flash, you basically not only load your program, but you also load all the parameters for your vector table. Now, how do I put code in the vector table? Well, fortunately, it's already done for you. STMicroelectronics provides you with this vectors stm32f0.c file that contain the typical function names that wants to be located for each entry of the vector table. All those functions are defined with a weak default definition and a while loop inside. What is that? The weak definition is yet another keyword from C, where if you redefine the same function somewhere else, this new definition will take control over the weak definition. If you have not defined the handler function, this will be the one that's going to be used in case we end up with an exception or an interrupt. So once you write a handler for a very specific request, you will have to use the same semantics that what was used in this vectors.c file. For example, this is a function that is defined in this file for the useart1 interrupt handler. Once you will write your own interrupt handler when you will deal with uart, you will have to actually implement this function manually. It will rewrite the existing weak definition that exists in this file. So fortunately for you, all this mechanism of putting pointers to the right location in your memory for your interrupt handlers is already dealt with, but you do have to follow the same naming convention that has been designed by ST. In order to process an exception or an interrupt, your processor must be in a specific state. So it's not always the case that you will process any request. In order to accept an exception, you must satisfy the following condition. Your processor, first of all, should not be halted for debugging. As you know, we can run debugger, stop our processor. Obviously, if the processor is stopped, we cannot jump into a new piece of code. Second of all, for the interrupt, as well as the SysTick IRQs, the interrupt has to be enabled. By default, all the basic exception, reset, NMI, and outfault are activated. They're fundamental to guarantee the proper operation of your processor. But for the other RRQs, you decide and you have to activate that by setting the right set of registers. In addition, the processor should not be running already an interrupt of the same priority or higher. Otherwise, your interrupt will be in the pending state. And finally, the exception should not be blocked by the prime mask interrupt masking register. So not only your interrupt should be enabled, but the prime mask should allow you to receive interrupts. Once we receive an interrupt, I mentioned that we are saving the context. Well, saving the context is no trivial task. And let us see how it's done. Once I get my interrupt, the context, meaning the regular operation that will allow me to resume that later down the road, must be saved. And our processor do use a mix of hardware steps and, if necessary, software steps. Basically, once you receive an interrupt, you will enter in a 16 clock cycle operation that will store your registers R0 to R3, R12, R14, PC, and XPSR that gets pushed to the stack. So the basic context is stored there. But now, you will, if you are looking at saving additional data, you will have to implement this additional software mechanism and push the additional registers of interest onto the stack as well. In addition to that, the link register is not updated with the return address as you would do in a regular subroutine, but it is updated with a special code indicating that once you will exit the handler, the link register must be popped from the stack. So you must actually load back this information from your stack before leaving the handler. So this is a very specific case that is different than the subroutine. Here's an illustration of the mechanism that happens when you do receive an exception. So when the interrupt line goes high, so when the interrupt occurs, it means that a bit is going to be set in our processor registers. Our processor will jump from the thread mode into the handler mode. In order to do that, the first step is to actually stack the information of your processor. As I just explained before, you stack the context, then you jump to your exception handler, and once you hit the exception return, you will unstack and go back to the main thread. In order, once you're done with that, or as part of the exception handler, should I say, you also do have to clear the interrupt flag to tell your system that you actually properly processed this interrupt. So as I briefly mentioned, the mechanism for saving the context is both part of a hardware mechanism and an additional software step. I told you that you might want to save additional registers, R4 to R11, for example, depending if you're using that or not in your regular main program. Fortunately for you, it's something that the compiler does very well. The compiler knows exactly which data are used at which point of time, and as a result knows which register should be saved or not when you jump into a function handler or not. The way it works is that it actually does not really know what needs to be saved, but it does know how much your interrupt handler is going to use as memory, and as such, it knows how much space it needs to free up. Now, what is going on when I do receive an interrupt when I'm already servicing one? Let's look at this following diagram. We have interrupt A and interrupt B, and we first start with interrupt A. So once interrupt A is triggered, I'm going to jump from the thread mode into the handler mode. And to do that, I'm going to stack my context from the main thread. My first handler is executed, and as usual, and once I'm executing that, I'm going to clear my interrupt service request, as you would do in a regular interrupt. But it turns out that before I ended up my handler, before I finished my handler, I am getting a second request for an interrupt. This interrupt has the same priority or the lowest priority, so the only thing I'll do is put that in the pending state, and this interrupt will be serviced once I am done with the first interrupt. This concept is called tail chaining, and this is a pretty useful mechanism as you remember, it takes 16 clock cycles to stack, 16 clock cycles to unstack, plus the eventual software stacking that you did. So we do that to avoid some extra restore and save of the initial context. So with this tail chaining, we are able to stay in the handler mode, deal with a second handler function, as you would do in the regular interrupt. So you process that, you interrupt, you clear your interrupt, and then once you're done, you return from the exception, jump back into the thread mode by unstacking the context, and you're done. This works, as I said, when we have the same priority or lowest priority. Now, what happens when I do have my highest priority interrupt that is coming in? Well, I mentioned we are going to enter in this nested interrupt mode where our first handler is going to be interrupted and stopped. Here's an example. My interrupt A of low priority is followed by an interrupt B of highest priority. When I get my interrupt A, I'm jumping from the thread mode into the handler mode by stacking the context. While I'm handling this interrupt, I do receive my interrupt B of a higher priority, so I'm going to jump into the handler of B by stacking again the context of my handler A. I will process handler B until I'm done and will unstack the context of handler A, finish that, and unstack the main thread context. In order to know in which mode I am, like should I return in thread mode or should I return in handler mode, I will use again a special value in the LR register. So to sum up what happened with LR, I can either store the return or the link address when I will have a return from a subroutine, or contain a special code that tells me if I'm in the handler mode and need to go back into the main thread mode, I need to unstack and jump back to thread mode. Or if I am in a nested interrupt situation where I am in the handler mode and need to unstack and stay in the handler mode. So we have these three distinctions that are made in our link register. As I said also earlier, the NVIC has some memory mapped registers, and they are part of the system space. If you do remember, in our memory organization, the very top of our memory is what we call the system space. And ARM has designed that space to actually map registers that are used to control fundamental operation of your processor. So usually, those are the registers that are part of the processor core and not external to the core. This NVIC being part of our processor will be mapped to the system space. And our registers will be used to take care of enabling, disabling the interrupt, countering the priority, checking the pending results, and we have the possibility to either control the registers manually, as you would do for a regular I/O and what you commonly do in labs, or you can use standardized APIs to make your life easier. Let's have a quick look on how you could do that. Here's an example of the interrupt enable and clear enable register. As you can see, they're located at a given address, very high in the memory stack, so really at the top of your memory subsystem. And those are some interesting registers. Those are registers that you do not really write into them, but you do go and write a value that in turns will be used to set or reset the real register. And you do these mechanisms to avoid conflicts and avoiding to mess up with the content of your registers. How do you access this space? Well, as I said, you could directly perform some direct addressing. So you'll have the address of your register that you can cast into a pointer. You'll dereference this pointer and you write whatever address in order to clear the bit of interest. I would like to point you to this volatile keyword that I introduced a couple of lectures ago. the volatile keyword here tells our C compiler that this register can be modified by another mechanism than us. And well, it turns out that the way this register works is that you write a 1 into, for example, this register to set the bit to 1, and once this bit will have been set to 1, it's going to be going back to 0. So you write something, but then the processor automatically clears up what you wrote in order to somehow acknowledge that it was done properly. So this register is going to change in the background. This is not something you do control by your software. So this is why you have this volatile keyword to let your compiler know that someone else than him might actually do impact the values. Another interesting example of the NVIC register is the interrupt pending set and clear registers. Those registers indicate if the interrupt has been serviced or not. So it's basically a placeholder to store what are all the interrupts that you receive that needs to be serviced. As soon as you enter a handler, those bits will be cleared automatically. And I would like to point out that while those bits are cleared automatically, just the interrupt pending set and clear, the interrupt request bits will still have to be manually cleared. Those are just indication of which one did trigger the request. You still have to physically acknowledge that you have handled the request itself. I mentioned that priority levels are set on 4 different levels, but they are saved on 8 bits values for each IRQ. How does that translate in terms of registers? Well, you end up with this pretty weird organization where the IRQ priority levels from 0, 1, 2, 3, and so on and so forth are organized, are controlled at the byte level, but organized as words. So in order to access those guys individually, you will need 2 things. You will first need to use bit masking in order to control those guys, and you will need to only understand which location exactly you're going to address. So for instance, you can still do things manually if you want to set your priorities, and here's an example of how you could do that, where you will first get the data coming from your entire word, apply some bit masking to, for example, modify some inner part of your RRQs, and then write things back. Totally possible, but somehow a little bit cumbersome. You need to use bit masking fairly heavily. Another option for you is provided by STMicroelectronics. Once again, it's to use an API. So as part of the libraries that STMicroelectronics is providing, you will have all your different registers to be already mapped within structures. And in particular here you have, as part of the NVIC, you will be able to access the priority bits, the interrupt priority of this specific UseArt1 RRQ, and set its value to be 0, 40, 80, or C0 directly without having to go through the hurdle of implementing the bit masking manually.